At the end of this video, you should be able to explain how Newton's law of universal gravitation accounts for various phenomena, including satellite and planetary orbits, falling objects and the tides, and apply Newton's law of universal gravitation to solve problems. Chapter 7, Section 2, Newton's law of universal gravitation. Gravitational force. Earth and many of the other planets in our solar system travel in nearly circular orbits around the Sun. Thus, a centripetal force must keep them in orbit. One of Isaac Newton's great achievements was to realize that the centripetal force that holds the planets in orbit is the very same force that pulls an apple toward the ground. Gravitational force. Orbiting objects are in free fall. To see how this idea is true, we can use a thought experiment that Newton developed. Consider a cannon sitting on a high mountaintop, as is shown on the screen here. The path of each cannonball is a parabola, and the horizontal distance that each cannonball covers increases as the cannonball's initial speed increases. Newton realized that if an object were projected at just the right speed, the object would fall down toward Earth in just the same way that Earth curved out from under it. In other words, it would orbit Earth. In this case, the gravitational force between the cannonball and Earth is a centripetal force that keeps the cannonball in orbit. Satellites stay in orbit for this same reason. Thus, the force that pulls an apple toward Earth is the same force that keeps the Moon and other satellites in orbit around Earth. Similarly, a gravitational attraction between Earth and our Sun keeps Earth in orbit around the Sun. Gravitational force depends on the masses and the distance. Newton developed the following equation to describe quantitatively the magnitude of the gravitational force if distance r separates masses m1 and m2.
Isaac Newton realized that the force of gravity makes a small object, like an apple, fall toward Earth because Earth and the object are attracted to one another. Only the apple appears to move, however, because Earth has so much more mass. In Newton's law of universal gravitation, he explains that all objects in the universe attract each other through gravitational force. The mass of the objects and the distance between them affects the size of the force. Newton's law states that the force of gravity depends on the product of the masses of the objects divided by the square of the distance between them. In other words, if two objects are moved twice as far apart, the gravitational attraction between them will decrease by a factor of 2 times 2, which equals 4. So, the gravitational attraction between two objects moved twice as far apart will be 4 times less.
Newton demonstrated that the gravitational force that a spherical mass exerts on a particle outside the sphere would be the same if the entire mass of the sphere were concentrated at the sphere's center. When calculating the gravitational force between Earth and our Sun, for example, you use the distance between their centers. Gravitational force acts between all masses. Gravitational force always attracts objects to one another, as is shown on the screen here. The force that the Moon exerts on Earth is equal and opposite to the force that Earth exerts on the Moon. This relationship is an example of Newton's third law of motion. Note that the gravitational forces shown on the screen here are centripetal forces. Also note that the gravitational forces shown on the screen act on the Moon as a centripetal force that causes the Moon to move in its almost circular path around Earth. The centripetal force on Earth, however, is less obvious, because Earth is much more massive than the Moon, of course. Rather than orbiting the Moon, Earth moves in a small circular path around a point inside Earth. Gravitational force exists between any two masses regardless of size. For instance, desks in a classroom have a mutual attraction because of gravitational force. The force between the desks, however, is negligibly small relative to the force between each desk and Earth because of the difference in mass. If gravitational force acts between all masses, why doesn't Earth accelerate up toward a falling apple? In fact, it does, but Earth's acceleration is so tiny that you cannot detect it. Because Earth's mass is so large and acceleration is inversely proportional to mass, the Earth's acceleration is negligible. The apple has a much smaller mass and thus a much greater acceleration. At this point, you should be able to understand sample problem C. Applying the law of gravitation. For about 6 hours, water slowly rises along the shoreline of many coastal areas and culminates in a high tide. The water level then slowly lowers for about 6 hours and returns to a low tide. This cycle then repeats. Tides take place in all bodies of water that are most noticeable along seacoasts. In the Bay of Fundy, as is shown in your textbook in figure 2.3, the water rises as much as 16 meters from its low point. Because a high tide happens about every 12 hours, there are usually 2 high tides and 2 low tides each day. Before Newton developed the law of universal gravitation, no one could explain why tides occur in this pattern. Newton's law of gravitation accounts for ocean tides. High and low tides are partly due to the gravitational force exerted on Earth by its moon. The tides result from the difference between the gravitational force at Earth's surface and at Earth's center. A full explanation is beyond the scope of this course, but we will briefly examine this relationship. The 2 high tides take place at locations on Earth that are nearly in line with the moon. On the side of Earth that is nearest the moon's gravitational force is greater than it is at Earth's center, because gravitational force decreases with distance. The water is pulled toward the moon, creating an outward bulge. On the opposite side of Earth, the gravitational force is less than it is at the center. On this side, all mass is still pulled toward the moon, but the water is pulled least. This creates another outward bulge. 2 high tides take place each day at a given point because, when Earth rotates 1 full time, that point will pass through both bulges. The moon's gravitational force is not the only factor that affects ocean tides, however. Other influencing factors include the depths of the ocean bases, Earth's tilt and rotation, and friction between the ocean water and the ocean floor. The sun also contributes to Earth's ocean tides, but the sun's effect is not as significant as the moon's is. Although the sun exerts a much greater gravitational force on Earth than the moon, the difference between the force on the far and near sides of Earth is what affects the tides. Cavendish finds the value of big G and Earth's mass. In 1798, Henry Cavendish conducted an experiment that determined the value of the constant big G. This experiment is illustrated in figure 2.4 in your textbook. As is shown in figure 2.4a, 2 small spheres are fixed to the ends of a suspended light rod. These 2 small spheres are attached to 2 larger spheres by the gravitational force, as is shown in figure 2.4b. The angle of rotation is measured by a light beam and is then used to determine the gravitational force between the spheres. When the masses, the distance between them, and the gravitational force are known, Newton's law of universal gravitation can be used to find big G. Once the value of big G is known, the law can be used again to find Earth's mass. Gravity is a field force. Newton was not able to explain how objects can exert forces on one another without coming into contact. His mathematical theory described gravity but didn't explain how it worked. Later work also showed that Newton's laws are not accurate for very small objects or for those moving at near the speed of light. Scientists later developed a theory of fields to explain how gravity and other field forces operate. According to this theory, masses create a gravitational field in space. A gravitational force is an interaction between a mass and the gravitational field created by other masses. When you raise a ball to a certain height above Earth, the ball gains potential energy. Where is this potential energy stored? The physical properties of the ball and of Earth have not changed. However, the gravitational field between the ball and Earth has changed, since the ball has changed position relative to Earth. According to field theory, the gravitational energy is stored in the gravitational field itself. At any point, Earth's gravitational field can be described by the gravitational field strength, abbreviated little g. The value of little g is equal to the magnitude of the gravitational force exerted on a unit mass at that point, or little g is equal to the force of gravity divided by m. The gravitational field, little g, is a vector with a magnitude of g that points in the direction of the gravitational force. Gravitational field strength equals free fall acceleration. Consider an object that is free to accelerate and is acted on only by a gravitational force. According to Newton's second law, acceleration is equal to force divided by mass. As seen earlier, little g is defined as F sub g divided by m, where F sub g is gravitational force. Thus, the value of little g at any given point is equal to the acceleration due to gravity. For this reason, little g is equal to 9.81 meters per second squared on Earth's surface. Although gravitational field strength and free fall acceleration are equivalent, they are not the same thing. For instance, when you hang an object from a spring scale, you are measuring gravitational field strength. Because the mass is at rest, in frame of reference fixed to Earth's surface, there is no measurable acceleration. Figure 2.5 on the screen here shows gravitational field vectors at different points around Earth. As is shown in the figure, gravitational field strength rapidly decreases as the distance from Earth increases, as you would expect from an inverse square, based on Newton's law of universal gravitation. Weight changes with location. In the chapter about forces, you learned that weight is the magnitude of the force due to gravity, which equals mass times free fall acceleration. We can now refine our definition of weight as mass times gravitational field strength. The two definitions are mathematically equivalent, but our new definition helps to explain why your weight changes with your location in the universe. Newton's law of universal gravitation shows that the value of little g depends on mass and distance. For example, consider a tennis ball of mass m. The gravitational force between the tennis ball and Earth is as follows. F sub g is equal to big G m sub e divided by r squared. Combining this equation with the definition for gravitational field strength yields the following expression for little g. Little g is equal to F sub g divided by m, which is equal to big G m sub e divided by m r squared, which is equal to big G m sub e divided by r squared. This equation shows that the gravitational field strength depends on only mass and distance. Thus, as your distance from Earth's center increases, the value of little g decreases, so your weight also decreases. On the surface of any planet, the value of little g as well as your weight will depend on the planet's mass and radius. Gravitational mass equals inertial mass. Because gravitational field strength equals free fall acceleration on the surface of Earth likewise depends only on Earth's mass and radius. Free fall acceleration does not depend on the falling object's mass because m cancels from each side of the equation as is shown on the screen here. Although we are assuming that m in each equation is the same, this assumption was not always accepted as scientific fact. In Newton's second law, m is sometimes called inertial mass because this m refers to the property of an object to resist acceleration. In Newton's gravitation equation, m is sometimes called gravitational mass because this m relates to how objects attract one another. How do we know that inertial and gravitational mass are equal? The fact that the acceleration of objects in free fall on Earth's surface is always the same confirms that the two types of masses are equal. A more massive object experiences a greater gravitational force, but the object resists acceleration by just the same amount. For this reason, all masses fall with the same acceleration as long as you disregard air resistance. There is no obvious reason that the two types of masses should be equal. For instance, the property of electric charges that causes them to be attracted or repelled was originally called electrical mass. Even though this term has the word mass in it, electrical mass has no connection to gravitational or inertial mass. The equality between inertial and gravitational mass has been continually tested and has thus far always held up. At this point, you should be able to explain how Newton's law of universal gravitation accounts for various phenomena, including satellite and planetary orbits, falling objects, and the tides, and apply Newton's law of universal gravitation to solve problems.